Good morning. On the 3rd of March, zooming along, we will be continuing to go through Chapter 3. We'll be talking about the Hilbert transform today, which actually takes us back into Chapter 2 a bit, and single sideband and applications of Hilbert transforming filters. We'll also be looking just at AM modulation and demodulation, more demo type stuff that I was doing last week out of the notebook, where you'll get to listen to things. And that sort of brings up a point. Bryce is not here yet, but this is an 8-transistor radio kit that I put together probably when I was either a freshman in high school or middle school or something. It was in an electronics class, because as I looked at this, I said, yeah, this was something I remember. Remember last week I told you how my wife and I are going to remodel our house, so it's just a massive clean out of 40 years worth of stuff, and it's pretty ugly. That showed up in an area that I had no idea it was even in there. But the batteries were rotted out in it, and I cleaned the terminals, and I put new batteries in, and we got to move, I'm contributing some brand new batteries with the radio too, and it works. It works best if we take it over to the window over there and let the AM low-frequency radio signals get into the antenna, whereas when you get this far in with this much rebar and or not rebar, but metal studs, it's kind of a giant filter. So what did I do? I pushed back homework set number 2. I've graded about 1/3 of set number 3. I've got so many competing things going on, but I'm going to push on that as well as pack and junk. I've got nothing but really miserable jobs to do. I don't enjoy grading. I don't enjoy cleaning up the house and picking through, filling bags to go in a dumpster. And they're starting construction, though, today in the basement of the house. So what did I do when I pushed back the histogram? I put it under down in here, and I have to refresh this browser, but so this is now what it looks like. This was the first iteration, and now I've added in sets 1 and 2, and I'm just giving you more numbers that I gave you in Slack. I'm telling you the set mean was 76 on the first one, it's 82 on the second, and this is what's gone on in that combination of the two of them. It's kind of like, I was saying, it's kind of like a convolution where things are going to get, it's not really a convolution, but there's going to be it's going to fluctuate around. So I'll keep doing that, and if you have any questions, you can ask me about it. And if you don't turn in an assignment, you get 0. So, and I had somebody ask me yesterday, can I still turn it in late? Well, Saturday morning early, I put the solutions up there. So what does that mean? It's like I don't think I can really do anything. I said I could consider partial credit, but it's really like a decaying exponential in terms of what I feel would even be appropriate to do. So, and Bryce, yes, this is your radio. Take this. I'm going to take the cover off of it just to show you what an 8-transistor radio looked like back in the 60s. I was older than that. I wasn't in the 60s when I built this, but there's 8 transistors in here. They're little metal cans. There's RF, IF type stuff in here. There's a speaker and some transformers for the audio. I see 2 transistors right there. And you studied electronics. Did you remember push-pull amplifiers or push-pull gain stages? Is that something you can remember from electronics?
Vaguely.
Okay. That's what I'm guessing this is. I did find it on the internet, a description as an old radio, and there's still unassembled kits out there. I guess they sell them on eBay or something. But at any rate, these transistors, my figuring from just looking at them, is they were probably not even silicon. They were germanium transistors. The most valuable thing probably is the 4 batteries I put in there, brand new, because the old batteries had rotted, and you know what batteries do. They chemically, they leak. Has anybody ever experienced that? So I cleaned the terminals. It didn't really destroy anything except it leaked on one battery. So it does work. At break time, take it up over by the window. It's tuned to a talk radio station right now. And it'll be a lot stronger if you get by the glass. So at any rate, the reason why he's getting the radio is because he was asking me about stuff and I sent him stuff. So you could part that if you wanted to. But I don't know, if as soon as you cut things off of something and then you want to reuse them, you're at risk of, you know, cutting it too close or something else breaking. But you can decide. So we will be talking about exam 1 later in class, and I'll say more. It'll be towards the end of the period is when I'll be doing the review for the exam. So back over to this. I want to go drill into stuff later. What I want to do right now is just return to amplitude modulation. And I think I posted on Saturday or something that I would be putting up another assignment sheet. That assignment sheet will be due after a week from this Friday. It'll be due after you take the exam on Tuesday is the plan. And I am formulating problems for it, which might be something innovative that's not even in the book, because I want you to experience some other things. So I'm still thinking about that. I'm very conflicted because I'm supposed to be cleaning out the house. I'm supposed to be grading papers and working the part-time job I have. So I've got, you know, I'm overloaded, and you know what that feeling is. You just, if you jump too much from one thing to the next, you don't get anything done. So I'll see how that goes. And I have to create the exam, of course, too. And I've started to work on that, and we'll be talking about that. And it's possible when we do the review that you'll give me some good ideas for exam problems. I won't tell you what they're going to be, but I might get inspired based on something. Grading papers has been inspiring in terms of things that get missing. So before I forget, one of the things that almost everybody keeps forgetting to do is when they calculate energy or power, they don't put units next to it, and that's fairly disturbing. Put W or J. I mean, I'm just going to tell you right now, I'm planning on the exam. If I didn't take any points off for it, but I will take off points if I ask you for power, and I want you to tell me how many watts it is, not just a number. So. And we assume a 1 ohm system unless said otherwise. So last time we were looking at amplitude modulation, and the very basis of it is we're going to put, let's see, where did it start? Right in here. I guess it started right where I was looking at it. It starts by just saying we're going to put a message type signal. It could be digital or analog. And we're going to put a bias on that signal. And what that does is it carries through the multiplication here to produce pure carrier. So pun intended, carries through to make carrier. Not very funny probably, but at any rate, there is a pure carrier that gets transmitted. AC times cosine, the carrier frequency, sinusoid. And then the message signal gets brought in with a modulation index A, and then the message signal itself, in order to control the modulation index to make AM radio work successfully, we need to be able to know what the modulation index is so we don't overmodulate the waveform, and I'll walk through that again. But the definition of the normalized message is to divide through the message by the minimum value of the absolute value of the minimum value of M of t. So M of t is generally going to be a signal that's positive and negative in amplitude. So you find that minimum value, which is some negative number, and then you take the absolute value of it. And then you have the modulation index. In this waveform picture we looked at last week, you see the idea of the modulation index is that when A is equal to 1, the envelope of the modulated carrier will just be touching together, and that says it's at 100%. If it goes greater than 1.0, it will be crisscrossing through the zero axes, and that will be overmodulation, and then we can't be demodulated successfully unless we do coherent demodulation, like we did with double sideband. With AM, the idea is to make it simple and not have a complicated receiver. So this is just another block diagram showing you the idea of how the AM transmission works. You add a bias to the message, and then you multiply times the carrier. This is a kind of a trivia thing that I think appears in the book or is talked about in the book. It just tells you if you were looking at this waveform on the oscilloscope, and this is, I say it's trivia because unless you're working in the lab, you wouldn't appreciate this. If you're working in the lab, you'd appreciate this because you'd say, I can just look at that waveform, and I can, from that waveform, I can take the difference between the peak to peak and the valley to valley. So what is that talking about? Peak to peak is up here, down to here, so it's that peak to peak value, and then the valleys that are in the envelope, the valley to valley is from here down to here. So if you form this ratio, you can get modulation index. If you're an amateur radio operator, this would be of interest to you, and it certainly was of interest to me back in my days of youth, I guess I'll say, because when I was building a radio kit like that, and I built things with vacuum tubes. One of those is safely in my crawl space. I haven't looked at it for a long time. I don't want to dig it out of there, but has anybody ever contemplated a vacuum tube electronic device? They're interesting, they're fun, they're dangerous though, actually, because vacuum tubes run off of hundreds of volts. So when I was playing with vacuum tubes, I got shocked quite frequently. I mean, it's not like you're gonna be holding on to the hot positive voltage with both hands and having current flow across your heart, but it's still, you'll get zapped on one hand, and it's a strong tingly feeling. And some of you have experienced that maybe too, like pulling an outlet out and maybe getting your fingers wrapped around it, and you might get that buzzing tingle. Has anybody felt that ever? Okay. I really think electrical engineers should have some sensibility about it. Probably the biggest thing that happens when something like that happens is that you react and you pull back, and you can hurt yourself when you pull back. You might rip something on your skin, you might bang or something, I don't know. Fundamentally though, you do let go, because if you don't let go, that's, there's all kinds of bad things that can happen, obviously. So there's a calculation, and then we talked about the envelope detector last week, and we'll look at a different type of detector in the code in a little bit here in the Python code. But this is the simple envelope detector, and it's present in that radio that I handed to Bryce, a diode, a capacitor, and a resistor. And then generally you follow this with a DC block. So what you would be doing in analog electronics, you'd be coupling this into an audio amplifier that would have DC coupling, so it would remove the bias that's on there. Because once you get it halfway rectified, you've got it sitting on a pedestal of DC, and you have to remove that. And I showed you the SPICE circuit here, and how filtering it attempts to do that. It's hard with a first order filtering action of the diode to remove all of the carrier frequency. But the higher the carrier frequency is, the easier it is. So we'll be talking about frequency translation and mixing maybe towards the end of today before I do the review. But in frequency translation and mixing, you always move to a common intermediate frequency, and that intermediate frequency might be 455 kilohertz, which really isn't very high. In the olden days of AM radio, 10.7 megahertz is used in FM radios of old, still to this day. And then in satellite communications, they use 70 megahertz, so that's much higher if you were doing something with an envelope detector, which is still used today, definitely. not for AM radio so much as just sensing the power of a waveform. You can filter away the carrier cycles pretty easily the higher the frequency is, because the first order low pass can roll off, over many decades if the carrier frequency is high. This is just showing you what the spectrum is, and we saw that, and we'll see that again. It's composed of the double sideband portion and then the pure carrier portion. And I think what we talked about last week too is that because, let's see if I can make this thing work. Because this term is now added in to make AM, it's not just added in a small way, it's added in a big way. I mean, it's larger than the message because it's trying to give you the ability to use the envelope detector. So it was invented not to be power efficient, it was invented to be low-cost receiver aspects was the driving factor. And I think we're familiar with other things that you don't pay a lot of money for. You may have a lot of waste or other things involved. This just is part of the way radio came into being. So there is an efficiency calculation, and these will show up in the homework problems. I don't really want to dwell on it a lot because this is not such a popular modulation anymore, but on the other hand, it is still very, very popular. I think I was looking something up that the digital version of this is called on-off keying, where you just modulate the carrier with power and then turn it off when you want to send a 0 and turn it on. And I plugged this in when I walked into class and I said, RFICs using on-off keying, and there's 87,000 hits there that the AI and the web browser used to get this little report filled out. So that says it's very, very popular. I don't fly a drone or anything like that, but it could be used in a drone radio link. It could be used in any low-cost RF that's not Wi-Fi or Bluetooth, anything that's non-standard. It might be used in, like, my mouse here it's a Logitech mouse, and there's a dongle on the side of my computer. It might be used in that just to carry the RF modulated carrier, the digital information into the receiver. It's very popular in things like that. And again, it always sort of comes up to make something low cost. So the power efficiency is the calculation that takes and finds through this calculation right here the power in the carrier and then the power that's put into the sidebands. And the sidebands are what we talked about last time. When we do linear modulation, we have upper and lower sidebands. So you find the ratio, and this analysis here just says it boils down to a squared times the power in the normalized message divided by 1 plus a squared times the power in the normalized message. And the carrier power, AC, is just sort of dropped away because it's present in both terms. But this gives you the ratio then of the efficiency, how much power is in the top versus how much power is in the bottom. And in this form right here, if you just take and put it into the original message, M, not the normalized message, there's the power that's in the carrier right there. Actually a squared over 2, but again, the 2 is in both numerator and denominator, or actually you can see it, it's in here. So those 2's cancel out. Is this making sense? It's pretty simple. It's not super complex. When we go up into FM modulation, though, FM does not make the amplitude of the signal rise and fall with the message. Instead, it's changing the frequency or the phase. So the carrier signal can be a constant envelope, but what's going on is inside the argument. So it's the waveform itself, it's frequency shifting it or phase shifting it. Different character and different behaviors. Single sinusoid, we looked at that last time. a calculation of power. And here is a case where, just to review again, the normalized message was 1/2 because it's a cosine, so the cosine swings by plus and minus 1, but the power in that is going to be then 1/2 when we normalize it, and it is already normalized, so it's just a squared over 2, or 1/2. And then the power in the carrier, in this example, was 1 kilowatt. Wanted to set the modulation index at 0.8. So down in here, the individual calculations are done for the power in the carrier, power in the sidebands, and then the efficiency. But you could actually get at this from different ways if you wanted to. I'd have to go back and look at the numbers up here, but what we could do is we could take this information and just plug it directly in there if you wanted to. So we could look at the normalized message, or the message, I mean, and then what is a little bit more not so obvious from this is, if I was doing the calculation from this information, I would probably opt to go with the first form there, the normalized message. And then I would take the total power of the carrier and work that into the rest of the math. But in this case, I did it, I guess, in a more straightforward fashion. I just said, okay, power in the carrier is just going to be 1,000. For the total power, I mean, is 1,000. Yeah, okay, now I'm thinking about what was special about this problem. In this case, the total power is given as 1,000. So another way of writing a problem like this would be to say, what is the power in the carrier is 1,000 watts. I'm going to put up a modulation index of 0.8. What's going to be the power in the sidebands to support a modulation index of 0.8? So that would be reworking the math slightly. That's going to be things that the homework problems are going to do. Just working with these equations, though. And then you'll end up with a spectrum. If you were to plot it, you'll have an amplitude. In the amplitude spectral domain, you'll have AC over 2, and then the 2 upper and lower sidebands, which will be 0.8 AC over 4, and a 2-sided spectrum, as shown here. Any questions or anything you want to go through on this in more detail? I'm wanting to keep pushing forward, but I realize your brains, I don't want them. I want you to think about studying well for the exam, but I have to keep pressing forward so we don't get behind. I did do an example in here with a pulse train just to show you that you can get better efficiency if you put in a pulse train, but it's not a very interesting message signal. I mean, it's a pulse train which might be useful in a radar kind of application, or some application where you want to send a pulse train to somebody and get a return off of it. But I don't really consider a pulse train as conveying information. If it was a pulse width modulated pulse train, then it could contain control information, like in robotics, or it might be analog modulation. We'll look at pulse width modulation later, but just a fixed width pulse train is not something I want to send to anybody. Do you want to receive one? I mean, I don't think it has anything particularly exciting about it, unless we were embedding modulation into the width of the pulse, but that's going beyond the basic idea of AM. But this, again, just shows you more calculations you can go through and how you can get all the way up to 50% efficiency if you were to go with a 50% duty cycle square wave. This next topic, though, is the next topic in the Python notebook, and this, I will give you a homework problem on this, too. This just says, suppose in reality we have a signal composed of multiple sinusoids, or maybe it's a speech waveform. How can you get this normalized message? Well, this is just taking you in the direction of saying that it's not a trivial thing. And there are some of the homework problems kind of swirl around on this idea, but in reality, what you have to have in the AM transmitters, you have to have a way of estimating the normalized message based on measuring properties of the message signal itself. It might be a gain leveling circuit that senses what is the peak value, the negative peak of the message, and then calculate a scaling factor or normalize the message then with like an automatic gain control or leveling circuit at the transmitter. But as a step in that direction, just suppose you put in multiple sinusoids, which is what this example is, we would then have to find the minimum value, and that could be, we could lower bound it by just saying, okay, suppose the phases and the frequencies are such that the minimum is going to be the negative of the sum of the amplitudes. Does that sound reasonable? I mean, you could go no smaller than that, right? If all the amplitudes hit at a phase of 0, you'd get all those amplitudes in a positive direction and all the amplitudes in a negative direction. And the negative side of that would be the most negative value you could possibly have when you have a sum of sinusoids for your message signal. Again, I'm not saying this is an exciting waveform to receive. It's just an analysis model to say, let's just model our message as being composed of a bunch of sinusoids. So this is like a lower bound. But that worst case value may be too worst case. So, and it's going to depend upon the phase and frequency values. So a numerical search or a waveform plot could also be done. And I wrote a function in Python that just said, put in amplitudes, put in phases, and then plot enough samples of that waveform with some sampling rate associated with it so that I can see what that minimum value is. So here I just drew a picture for this particular value of 65, 100, and 35, and I'm doing a sampling rate, I guess, of 1,000 hertz. And there's what the waveform looks like. So in the case of my analysis model, I have right in here that I would add up just all of those amplitudes, the peak amplitudes, and take the negative. So the worst case would be minus 9.7. But do I achieve that in practice for these phases and frequencies? No, it actually ends up being a not so negative value. So that would be rather pessimistic. So it's actually 7.2 is the normalization factor. And then just to prove that that does indeed produce a waveform that abides by the modulation index, these three plots here just show the modulated carrier, and showing the envelope is red. And it shows you on the third plot there, when I set the modulation index equal to 1, I'm just touching right here. So that means I'm at 100%. And I didn't put a nice legend on here. I did put the, I guess I put the values off to the side. 0.25, 0.5, and 1.0. So it's just a way of setting the gain. And if you were building a transmitter, you'd want to have some means of knowing that you're not going to overload. And if you're working in the lab, you will have a modulation depth control on the generator. I don't think you did that yet last week. I'm trying to remember. No, but you will have that in the generator. But that's for a single sinusoid. So otherwise, you have to approximate it and have, like I said, some circuitry that scales things accordingly. Maybe this gives you an idea of why in broadcasting, and this is kind of off to the side, but not really totally off to the side. Suppose you're listening to a sports event and announcers on AM radio, and sports is still a popular means to broadcast using AM radio. Talk radio is probably the biggest thing, and the station that I have it tuned into right now on the radio I gave you, Bryce, is a talk radio station in Colorado Springs, and they're going on and on about what they always go on and on about. They're generally talking probably today about Iran and what's happening over there, and they're talking about other, political-oriented types of discussions. So that's what talk radio does. Sports, though, when you're listening to a sportscast, like if you're listening to a baseball game, let's say, or basketball or football, you always feel like the announcer is very loud. And if they stop talking for a few seconds, you hear a background rise in the background noise. Has anybody ever noticed that? It's gain riding on to keep the mic level so we can keep the modulation index as high as possible, because that allows your signal to be heard. If any of you used Citizens Band Radio, which was a popular unlicensed radio spectrum for truck drivers and just talking amongst your family, you might have FRS. Does anybody know what an FRS radio is? Family Radio Service. It's a free radio, unlicensed band you can buy radios for. They're useful for, I don't know, I've used them in car chains, like if you're driving 5 cars to go to the mountains to go fishing or whatever you're going to go do, or you're at an amusement park. My wife and I used them once at Disneyland, and we were separated so we could talk to each other on a radio. But it's unlicensed, so anybody else can use the same frequencies, and there's only a finite number, so there's no guarantee. But similar idea, and they use amplitude modulation originally with Citizens Band Radio, which is morphed into Family Radio Service. It's also used in hunting, I guess, too. If you go hunting and you're at your post where you're going to sit and look for the deer to come by, and your friend is somewhere else, you can communicate something. At any rate, keeping the gain level up high is generally the objective in amplitude modulation, which is why it's not very good for music, because that music requires dynamic range, whereas in AM radio it gets staticky and weak sounding. Like up here, this with a little bit of noise in the background beyond this signal, this would not be as clear as the higher modulation index, but you have to keep it from overloading, so that's what the audio compressor does in a broadcast situation. It just keeps it pumped up close to 100% so that it punches through any background interference, and it rises up the gain when this person stops talking. So in this particular case, with this example again, and multiple sinusoids got up to 24% efficiency. And this is what the multiple sinusoids case looks like spectrally. And this is kind of a nice picture to show you the perspective too, because now if you think about having the amplitude modulation of, say, audio like we had in the examples last week, it would just be more of a continuous spectrum at the positive frequency, let's say, and upper sidebands, lower sidebands, and then up through the middle is that massive carrier. The carrier is just huge because it's trying to make sure we're staying, and this is at 50% modulation index. So if we went up to 100%, took A up to 0.5, this would come up a little bit, but still it would be, the carrier is just massive. So I'm trying to impress upon you the fact that with AM, it's easy to receive it, but we're putting a lot of power into the carrier. Not enough to fry your brain when you're a long ways away from the transmitter, but friends of mine, I worked for a company, Paracle Communications, and what's up on top of Cheyenne Mountain is not AM radio stations, but TV stations and FM broadcasting stations. And there's a high flux density from all those transmitters. And I didn't have the experience of going up there, but they would go up there and do some maintenance and other things for the antenna sites themselves, and you were only allowed to be on site for so many minutes for safety reasons, because the flux density is high. That makes sense? Why is so much density or such a high power, trying to broadcast to the whole Pikes Peak region and make people happy and allow the broadcasters to sell advertising so they can make money with their radio station. Okay, now we're going to move off, and we're going to go look at single sideband, but before we do that, I'm just going to check, because I don't remember exactly what I did in the notebook. And this is the exact example we just went through in the notes. So here I put in the function, and you can see the sampling rate is in there and the number of samples, and I used that to create the waveform, and then I just simply used an operator in Python to find the min. So I just found the min using min itself. And this is the old formatting system rather than the F strings that we've been looking at. So this is the help on that function though, min, and there's a max, and they're NumPy functions. So then I did a calculation of the power, and interestingly enough, or maybe not so interesting, I kind of took this a little bit crazy, but I said in 2610 you can find out the power of a sum of sinusoids as long as the frequencies are unique. You can just sum the power in each sinusoid, so it's the a squared over 2, but then we're dividing by the peak, the normalization factor here squared, and we get 0.3227 watts. I also went ahead and said, well, what is going to be the power in that? From a statistical standpoint, we can just get a power calculation done using the variance operator. The variance estimator actually is what it is that you learn about in probability and random variables. So the variance, just take that message signal normalized, and that gives us the exact same number. And then if you want to say, okay, I want to put all the power and might that I know about from my calculus background, I'm just going to find the average power by integrating. And so I integrate over one period, or just a long period of time is really all I'm talking about. I'm just going to find literally what that quantity is right there. I'm going to take the normalized message and I'm going to just run it out for a long time and just say I'm going to average over, in this case, 1.0 or 1 second is what it amounted to in this case with the model put together. So the average power over a 1 second interval, I get the same answer. Now all of these are, this is more of an approximation because it's a numerical integral, all right, but I may have to use a longer window to get the true estimate, whereas the first method was exact because I knew the frequencies were unique. Second method is also an approximation because it's just based on how long the measurement interval is. And I could change that. I could make it shorter or longer. I kind of put this in, though, to let you know that you can resort to a numerical integration if you choose to do so. And here I just created an integrand that would go into the numerical integration. And I don't know, what's your background? Have you done numerical integration for any homeworks or anything in another class? Okay. Yes and no. Numerical integration is just a tool that's at our disposal, and sometimes it's very handy to be able to use it, and there's a variety of functions. There's a whole package. This is the SciPy integrate package. It's so up at the top here. I imported, I guess I didn't import, I imported it nearby here though. Drop down in here where I just was. I think I imported it in here somewhere. Yeah, there it is. It's right in front of me. So I imported from SciPy the function called the package called integrate, and I just gave it the name of integrate as its abbreviated name, and then quad is a numerical quadrature function, which I'm not getting any help on it right now. Sometimes to get it to go, you've got to try this again. Nope. Okay. I know why. I didn't run this originally, so still not working. There we go. So the integrate package has got a fair number of functions associated. We're just using quad. So what is quad? Compute a definite integral, and it uses a Fortran library under the hood in Python called QuadPack, which allows us to set up a numerical integration, and we can set up accuracies and how it's going to partition the function, the integrand. So numerical integration is not like we played around with earlier, where I just said let's do a simple rectangular approximation. You know, that's when you first learned about integration in calculus, you had the rectangular partition. Quadrature can do things a lot more sophisticated, so there's a lot more knobs to tune, and when there's more knobs to tune, there's always the chance that these default values that you see in here will not necessarily work. You might get an error message. I mean, a lot of you experimenting with Python, mostly doing good stuff from grading the paper, grading your papers, but you can get into trouble with any numerical algorithm where it might fail, and it might give you a warning like it's not converging or whatever, or it might just say, I can't do this numerical quadrature because the function is too widely varying. So just be wary that I picked a really simple case, and it worked, you know, really, really well, but I had to set attributes and things in the function, and then I set the integration limits in there too. So you can see that I'm integrating over 1 second, but I'm setting a lower limit and an upper limit in there. I'd love to say go play with it, but play with it in your spare time, which I know you have very limited amount of, but you may bounce into numerical integration. What we do and what I do in my work, I mostly just do the simulations like we're talking about. A simple rectangular integration, which is very easy to set up without using the integrate package, and then maybe use the power spectral density estimate to get the fractional bandwidth. I didn't have you do that in the homework problems that you just turned in, but we could have also done that too. I mean, that's just quicker, and typically it's accurate enough. But this is always at your disposal if you wanted to get more sophisticated. So then I went ahead and plotted the line spectra, just going back to the fact that it's sinusoids, and I could get the line spectra based on the known spectral lines for distinct coefficient or distinct sinusoids, and then I went back and resorted to using, I created a function to plot the spectra. So that's what this function is doing right here, and that's how these plots were obtained. If I was to do that today, I would probably just go for the power spectral density. So maybe I should do that so you can see how I'd prefer to do it today. So up here, I created this. Let's make sure it's still created. Let's see. So then what I could put into here, I could put in M, or I could put in, I could put in the complete carrier Well, actually, how did I do this? I have to think about this. Maybe I shouldn't be wasting my time on this right now. What I was going to say was I was going to plot just the power spectral density, but I need to create the AM waveform. And this is, I've been using this a lot. This is a function that's in the SIG-SYS module. But I'd want to do it on the complete carrier. And here I rolled it up inside of this function that does the multitone spectra. So I guess at this point, maybe I don't want to do that in an example. We could tear this apart, though, if we wanted to. There it plots the spectral, it gives you the spectral lines, and then it gives you, lets you plot the spectrum itself. What I could do, though, I'm just rereading my function because I didn't remember what I have it do. ACFCA index. What I was going to do is I was going to go hack this function slightly and just take out a copy of the waveform. But I have to do a little bit more hacking than I want to do right now. I'd rather start from scratch. Do you want to see an example of how I would do it from scratch, just to get a flavor for how it might work? Because I want to encourage you to try building simulations, but there's a time for simulations and there's a time for analysis. And example was the grading that I finished last night. I didn't want simulations on certain Fourier transform problems, so I wanted you to do the math of the Fourier transform in the F domain. Some people were using omega. I wanted you to use frequency in hertz. The Fourier transforms were as we have defined in the book. Checking, though, with a problem is always a good thing to do. So what I could do, let's hack into this example up above here. We have, rather than putting in the phases like I've done, I'm just going to put in frequencies, amplitudes. I'll take all of this stuff here. So I'm just going to create 10,000 samples, and I'm going to create my AM signal, or I'm going to create the message signal M as I'm just going to manually write this in cosine of 2 times pi times I'm going to sample at 1,000 samples per second, which is what I did before. So I'm going to create a time axis that has delta t at 1 over 1,000. So I can put into here 65 hertz times t. And then I wanted to put an amplitude of 2.0 on that, and then I'm going to create a second term over here, which is going to be 3.5 times cosine of 2 times pi. And I guess I'm just going to put the phases into, I had 0, and then over here I have 2 pi times 100 times t, and I had a phase of pi over 3 on that one. And then the last one is going to be 4.2 times t. Now, frequency has to be in there, and that is was that 4.2? Now I'm losing track. 35. Okay, that one was 35. Plus or minus pi over 4. So before I move on, and this is just kind of a good practice that I have, let's just see what I've created. Okay, I have a lot of cycles in there, so I can temporarily dial it down, or I can just go over to here and say I'll just plot 1,000 cycles out of the 10,000. Oops. I didn't do that over here. Okay, so there's what the composite waveform looks like. And now I can create a modulated carrier, and in reality I probably would like to take this up to 10,000 hertz so I can put the carrier at a frequency that's somewhat above. So I'm going to create my X sub AM, and right away, what can I see from this plot that I made over here already? I did this in the previous model, but what do we see the negative values are swinging down to? It was minus 7 point something, right? That's what this analysis up here did. It said the minimum value was minus 7.2. So I could do a quick check on that if I wanted to too. I could go ahead and just throw in another quick test here and just say what is the min of M. Okay, so now with this sampling rate it's saying it's minus 8.77. I guess I must have changed some numbers in here because it's dropping down further. I'm not going to argue with it because maybe I just entered something differently here. So now I can put in an AC value of 1.0 times 1 plus 0.8, and I'm going to normalize by that min value of M. But it has to be the absolute value, so I'm just automatically going to normalize my message right here, and then I'm going to multiply that times the message. And now I'm going to put in a carrier, and I've got frequencies for the message tones that are at 65, 100, and 35. So I'm going to put my carrier up at 1,000 times T. I've increased my sampling rate to 10,000, so I know I can go up to a folding frequency of half of that, which is 5,000, so that should be adequate. I could actually dial this down slightly. 1,000, maybe make this only 8,000 rather than 10,000. So now if I look at my composite over here with the carrier included, which is XAM, I'm now seeing the carrier cycles. I'm seeing the 3 tones of message signal fluctuating around. I'm not at 100%, or am I? Just look at the waveform. Is the envelope closing in the middle? Remember peak to peak and valley to valley, so peak to peak and then valley to valley, but it's not the smallest valley to valley is still greater than 0, right? So did I even succeed at getting there? Suppose I increase this up to 1.0. I'm still not quite there. It's very close, though, in this particular case. I probably should run over more cycles because I'm aperiodic, or at least it's not, the period is long. So for all practical purposes, it's not 100%, but it's pretty high modulation index because I can see the valley to valley is getting very close to 0. Everybody following what I'm saying here? So now I can go ahead and drop down here and say, let's just take a look at the spectrum of this waveform that we created. We'll use all of the samples and maybe even then some. So we'll do X type underscore tab. I have this guy that was created. I'm going to go with a 2 to the 12th transform, and in terms of my other attributes, I'm going to set Fs equal to what it was, and what was it up here? I didn't set it, I put it in numerically as 8,000, so I'm just going to put it in as 8,000, and hit Shift Tab again, and I'm going to leave the overlap percent in this spectral calculation at its default value, and I'm not really telling you how this is working, but it's basically doing what's called an averaged periodogram, but it's averaging by overlapping some of the segments of data because it's using a window function which tapers it, so I can get by with using the data a second time because I'm tapering it down at the edges. So that's what the 50% does, overlap. But I'm going to set the scale factor, scale noise, I'm going to set it equal to false because then it's going to attempt to do a spectrum that has the true power of the sinusoids scaled properly. So I'm going to put F sub AM, and this is a power spectrum, so it's 10 log base 10. And it's a real quantity because it's a power spectral density. It's not a complex quantity. And there it is. I don't like the looks of my axes plotting, though. This is all just washed down here from the FFT and the fact that I don't have noise present. So whenever you see something like this, don't give that to me. And some of you, I said zoom on the horizontal axis when you're doing the pulse shaping because you wanted to see the spectra of the root raised cosine pulse shape. Here we have way too much dynamic range to really be useful. This is just artifacts from the FFT or the transform. So I'd probably drop this down to maybe -80. So what I would do in my scaling over here, I would go y-axis, pick it up at -80. It looks like 0 is a good top number in this case. And I'll turn on a grid. And if I put a semicolon at the end, it'll suppress this display of the matplotlib address and everything. So, wait a minute. What did I do? Oh. Oh. It's ylim. Okay. So now it's looking pretty good, and now at this point I'm inclined to say, well, I'm only at 1,000 hertz. My tones are pretty closely spaced. Why don't I just zoom in on this? So why don't I take and put an xlim on here of maybe 500 to 1,500 or 750 to 10,250. So I'll go 750 hertz, 10,250, or not 10, but that. And then if I'm not happy with the sharpness of this, it just says I'm not using enough FFT points because I'm getting kind of not really razor sharp peaks. So I could increase the spectral resolution if I wanted to. And to do that, I could go up here and I could just say, okay, I'm going to take this up to maybe 14. And okay. So what's happening? I'm running out of data is what's happening. I know that error message, it just says I'm getting invalid value encountered in divide. I don't have enough points in my simulation, so I'll bump this up to a massive number of 100,000. And then I can run down here. And now I have enough data to drive my spectrum analyzer. So that little glitch is the fact that in order to do nice detailed spectral analysis, I have to have a really long time window so I can drill in the frequency domain. And now it's looking much better in terms of the modulation index. I'm supposedly at 100%. Let's just get a feel for what happens if I do drop this down to a lesser modulation index. I was running at 1.0, but suppose I put it down at 50%. And take a look at this again. You see, we're not modulating as deeply, and we should see the carrier is not is up higher at this point. I guess if I go back over here to the notes, I'm realizing that I said something that was misleading over here. I said the carrier is much higher than the sidebands, but what's my axes on the Y side? It's not a log scale. So that tends to accentuate the fact that there's a huge difference in amplitude. If I'm doing it in terms of power, though, I'm taking 10 log base 10 of power. So in the simulation model, we're seeing it in a better light, I guess. If I was to take this out of here, let's do this. Just temporarily take that away and just put PAM in here. Then it's going to screw up the scaling, but I'm just going to throw it in here and see what happens. Chances are I'm going to have to change that. Yeah. It's gone, right? Now, what I have to do is I have to do this, comment this line out temporarily, and just see where it's at. So I'm not even going to bother to rescale it because this is actually pretty good value. So now you can see at 50% modulation, the little sidebands are way down. The carrier is just like poking. It's like a tent pole, right? You're in a circus tent or something where you got that single pole, and then the people that are inside the tent maybe are the spectral lines. I'm just being creative sounding, but it's way, way down there. So this is reasonable, I think. We could go ahead and see how well this is calculating the power in dB for our carrier if we wanted to, but I think I've kind of let this run its course for now. Put that back. Oops. What's going on here? Oh. Fell into my Macintosh keyboard mode for a second there. If you use the different operating systems, you have different keyboard commands. But there we are back again to where we were before. And this should be approximately power in dB for a two-sided spectrum at this point. So we do have a negative side to this. So now that I'm thinking of this, how could I get the negative side using this PSD function? I'm putting in a real function, so my PSD function here says, oh, if I'm putting in this as a real quantity, the negative spectrum is always going to be the mirror image of the positive one. In some cases, in DSP and COM signals, we have complex waveforms, and we're heading into that with the Hilbert transform. But how could I temporarily, as a quickie thing, make it think it's a complex signal? What could I do to just fake it out a little bit? I could take that real signal and I could put a 1J in here times 1E minus 6, let's say. Just put in a really tiny imaginary part. Should that work? What do you think? It's gonna make it think it should be two-sided. So, but what did I do wrong here? Oops, I deleted something, it looks like. And this was X AM. It didn't work. Oh, I know what's wrong. I scaled this guy to be positive and negative, so let's make this start at minus 1250. Okay, there it is. So now we're seeing it as a two-sided spectrum just by letting it know that it's possibly complex, but it's really insignificant. It's very symmetrical looking. Good? I'm not trying to bore you to death. I'm just trying to let you know that you just let your mind and your fingers on the keys just, work things around and be happy and strive for something that looks good and makes sense. I mean, I wouldn't put this in notes probably unless I wanted to emphasize it's symmetrical. If I was wanting to emphasize what the peak values are, I'd want to just look at one side or the other so I could convey more information. Okay, so let's go back to get ready for the next demo. We're going to look at the Hilbert transform next. So we're going to go back to the notes. And what is single sideband modulation? This was popular a long time ago. It's still in use, but it's not nearly as popular. But it is still, a form of it's still used, and we'll talk about vestigial sideband here in a moment. But single sideband says that, well, if we're transmitting double sideband modulation, it's called double sideband because we always end up with two sidebands, upper and lower, and they contain identical information. Why are we doing that? Convenience, mostly. But if we wanted to be more efficient, we could transmit just one of the two sidebands, and then we could pack more signals together. Remember, we talked about spectral occupancy as being, or spectrum as being a natural resource. So the telephone company a long time ago realized that if they wanted to have a network in the analog domain, they could have a switching center where they would use single sideband and they could pack as many telephone channels together as possible and send them around the country, or send them around a community with wires, twisted pair wires. So they had the idea of using single sideband from way back when, and then it became radio airwave type broadcasting too. So the idea is to, pictorially, it's to do this. Take the message of bandwidth W and remove either the upper sideband or the lower sideband. And that's what this picture is just showing you. In order to show how to do this, it's best to do it by understanding the Hilbert transform. And the Hilbert transform is a special type of filter. It can be an analog filter, it can be a digital filter. But before even mentioning the Hilbert transform, you can just say, from my understanding of filters, why don't I just build a very narrow bandpass filter that just allows one sideband to pass and block the other one? That can be done. That's challenging, and that becomes part of the dilemma of going with single sideband, is how to filter it. So you need higher order filters to do it. But the Hilbert transform also has other applications, and so we jump back to chapter 2 for a little while to describe what is the Hilbert transform and how does it give us single sideband signals. So the Hilbert transform is a filter that shifts the phase of all frequency components by 90 degrees. Mathematically, and this is fundamental to understanding it, it's a filter, and it's not realizable identically like this because we can't build it and make it causal, but we can approximate it. This is the nature of the Hilbert transforming filter. Because phase on a real frequency response has to be an odd function, we end up defining the phase response, the 90-degree phase shift, with this function called SGN, signum function is the name of it. And in Python and MATLAB and so on, it's SIGN is the name of the function. So we have it available in our toolbox as well. But SGN is the mathematical terminology, the signum function, and it's a piecewise function. So it's a function that's positive, 1 for f greater than 0, and -1 for f less than 0, and 0 at f equals 0. So this applies that phase. If we put it in the context of -j out in front of the signum function, means it's going to be 90 degrees on one side and -90 on the other side. So if we write it if we call that the Fourier transform of the Hilbert transform and view it as a convolution with an impulse response, we can actually go backwards by inverse transforming this frequency response and establish that in the time domain, and I'm just sort of stepping down through this, we can get this next blue boxed equation, which says that 1 over pi t is the impulse response of the ideal Hilbert transforming filter. I'm just displaying that. I don't really ever suggest that you want to work with this because this is not an easy function to work with. 1 over t is a singularity, right? And then put that in an integral, like a convolution integral, and it makes things messy to work with. For our purposes, we're better off just thinking that it's a filter that has this 90-degree phase shift property. And we'll be making use of that over and over again in this little section of notes here. So this is not something that we're going to do. But if you wanted to mathematically represent it, that's how you would do it. It's better, though, to just think of it, like I said, as the phase shift. So this example right here just says if you phase shift by pi over 2, that says that if you do 2 Hilbert transforms, cascading 2 filters in a row, you'll shift by 180. And what does 180 do to any signal? It's inverting it, right? So this property right here follows, and you're not seeing double with your vision. It's really on the page. I have 2 hats on the page. By the way, that function that produces the hat in LaTeX, which you use in the Jupyter notebooks, it's /hat, but the mathematical term for it is circumflex. I find it kind of bizarre that it has such a, introverted sound like circumflex. I don't know the history of it. Maybe if you're interested, study up on it. But in languages like the typesetting languages, hat is much easier to say. It's just a hat on the top. So we have that. So if we have a cosine and we take the Hilbert transform of the cosine, we're going to get a sine because we're going to have this minus j signum, and that's going to propagate around minus j and plus j. And if we put that back together with Euler's identity, that's a sine. And then we get this operation here, which makes sense. 90 degrees phase shift converts a cosine into a sine. And if you take the Hilbert transform of the sine, it's like taking 2 transforms of the cosine, so you're going to get back minus cosine. So you have this property too. These are just a few of the simple cases, and they're the things that really matter most to us right now in just getting the understanding going. So because it's a phase shift only filter, it does not alter the energy, the power in a waveform. And that's the proof of it right here. It's also interesting that the signals are orthogonal to each other in the sense that if you multiply a x times x hat and integrate it, the integration operation here is a form of inner product that you learn about in abstract linear algebra, which you had linear algebra at one point, most of you, right? Remember abstract vector spaces? So in physics, it was the dot product between x, y, and z coordinate vectors, but in mathematics in general, the abstract vector space idea would just say x is orthogonal to another waveform, say x hat, if the integral of the product, and so this is forming as an inner product or dot product, is equal to 0. And then here's a more extensive proof, and you can apply this through generalized Parseval's theorem, which you can take two different types of signals in. So Parseval's theorem generally says you take x times x conjugate, but you can take x times y. So in this case, we have the conjugate operation going on in here because of the Hilbert transform. And we end up with this odd function times an even function, and that's going to integrate over symmetrical limits about 0, and that will integrate to 0. So that's the proof of the orthogonality. For our purposes in Hilbert transforming and creating single sideband signals, we also have this. This is probably one of the most important properties that Dr. Ziemer talks about in the textbook. Message is going to be band limited to say W hertz, so it goes to 0 above W hertz in bandwidth, multiplied times a cosine that's like a carrier frequency, or just omega naught t, where F naught is greater than W. Then we see this orthogonality relationship bears out as a special case of saying that Hilbert transform of the product is just the signal that's band limited times the Hilbert transform. So we get this result. And that's a useful property as well in creating a modulator or demodulating. The next idea, which will take us up to the break time, is what is an analytic signal? And none of you have taken, I don't think, a course in complex variables yet. You may do it in graduate school. I'd recommend it if you're a master's student and above. I did. I took it at Michigan Tech, actually, when I was getting my master's degree. It really was insightful to learn more about complex variables. And why did I want to do it? It's because EEs spend so much time with complex numbers. And I thought, this will be fairly straightforward. Turns out, you know, we're only scratch the surface of complex variables in electrical engineering most of the time. So we study a lot of properties of complex functions and an analytic signal is one such signal that we bump into. So the electrical engineers take over just a portion of it. They say an analytic signal, for our purposes, is defined in terms of the Hilbert transform. It's x of t plus j x hat of t. So it's a complex waveform, assuming that x of t is real. The envelope of this complex waveform is the envelope that we were seeing in double sideband and in AM. And this actually is very valuable, and this I'm setting out to have this incorporated into a homework problem that I started working on, and said, no, I have to grade papers, no, I have to pack stuff, you know, all the stuff I was talking about over the past few days. But this just says if we can take a real signal and form an analytic signal, we can easily get at its envelope without having to think about using a diode. We can do this in DSP. We can form an analytic signal. So the analytic signal has value there, and it also will show up in a couple of homework problems just to study how it relates. And in particular, for right now, we're talking about using an analytic signal to see that it does indeed have single sideband characteristics. So if we form a standard analytic signal where we just take x and x hat, we will have, because of the signum function being positive and negative, it switches at 0. We get this going on here. We end up with just the signum function. When we bring the j and the minus j together, we have j times minus j is 1. So we have 1 plus signum. And if you remember, the definition of the signum function is it's minus 1 for f less than 0. So that means these two terms annihilate each other and we get 0. And then we get double on the positive frequency. So that has the character of a single sideband signal. It's at baseband, it's centered on 0, but this tells us how we can do things with an analytic signal to form a single sideband. And this is just showing if you put the minus sign in here, we'll get the negative frequencies only. So we have the z sub p and z sub n forming upper and lower sideband signals. I know you're probably thinking, this is so bizarre, why do we have to do this? Well, you're engineers, so you know that you have to do hard things or take and stretch your brain to learn new things. I'm thinking about the guys that are going to be ripping out all the popcorn ceiling in my house, which is a mess, and then re-drywalling the ceiling and all those things. That's a trade, and you could be doing that too, right? Maybe, maybe that's fun. I don't know. Has anybody ever done that in the summer? Is it acceptable employment, mostly? I'm just curious because I've had people in this class that have been framers. I don't know if they've done drywall for a living, but I mean, people, you move through your life and you decide to do different things. So I don't know of anybody that's studied to be an EE and wants to go and become a drywaller after they've gotten their EE degree, but some of you may have done that for a summer or worked with it. When I was first done with the university and started working and then I got terminated, I started learning a little bit about drywalling because I wanted to fix some holes that were in walls or damaged drywall, and I got into it, read about it, bought some tools, and realized it's messy stuff to work with because that drywall powder that's why we're leaving the house, because the house is just going to be really bad. At any rate, that entered my mind thinking that I'd rather do this because it's meaningful to me in my own way, but the meaningfulness to you in your life with your work is always going to be considerably different than what the average person would do. It's your thing, they have their thing, and your thing gets you a job and pays your bills and so on and so forth, just like their thing does the same thing. But people just don't relate to this really well, right? Drywall they know because they have it. This is going to be more abstract pretty much all the time. So going back to single sideband development, we want to have a sideband filter that can take, say, double sideband, which is what we have on the left side there, message times cosine. Why is that not AM, by the way? Just to make sure you're learning something since last week. You see that we have a message times a carrier, and that was the simple double sideband. We would have to have a pure carrier added in to make this AM. Now, the pure carrier could be hidden inside of M of t as a bias term there, but we're assuming we're starting with double sideband, no pure carriers being sent, and now we're going to produce a sideband filter to get either the upper or the lower sideband, and we're going to try to use the analytic signal idea. So we could build the double sideband filter just from scratch, just saying we're going to build a filter that only passes the upper sideband. But is there some advantages or some added understanding from thinking of analytic signals? So that's what the book talks about, and I'm not going to spend very much time on it because it's just not that common to want to produce a single sideband signal. They're still, like I said, they're still used. Amateur radio people definitely use them. They're used in some ship-to-ship and ship-to-shore communications. There might be single sideband still in a standard. Whether or not it's used very much, I don't know. I would think most commercial shipping is going to use newer standards for everything. But what have I talked about at various times? Legacy, and you're going to work for like aerospace companies, you're going to be in legacy all the time. You're going to be something legacy. Why do I see this in my work? It's because we're building a new version or supporting some legacy something or another. So you just have to come to accept that fact. We don't always start with clearing the deck and putting in all new technology. So how this can be done, though, is you can start, and this was just a picture that I created to kind of explain in my mind the math that's on the next page. But I'm not really going to go through the math. I'm just going to say, looking at this, we see that if we had this double sideband signal, if we could form using signum functions, the first signum function there turns on or switches on in the frequency domain at minus FC, and the second signum function switches off at plus FC. So if we were to build those up, we would have this perfect filter that would only pass the lower sideband. It would be sitting in here on the plus side and sitting in here on the minus side. Does that make sense? We could use the signum function, which is the core of the Hilbert transform. And we could do the same thing. I don't think I didn't repeat the picture. We could do the opposite of that to maintain the upper sideband. So the way I write that out is I visualized it as taking the message, frequency shifting it up and down, and then putting the signum function, wrapping it around it here and here, and doing some rewrites of the math. This is just, for me to go through it, it's going to put you to sleep, and for you to think about or grab it instantly, you just have to, it's one of these things you just have to stare at it and kind of draw your own little pictures on the side. What it comes down to, though, is we do a couple of rewrites of that with the signum function and the shifting, and we end up getting this as the double sideband, and then we roll inside of it the signum function on M of F and do some more math, substitutions inside of there, and what we end up with in the end are these two equations. The first one says we take the signum function of M times the sine, and then we have the signum function, then we have the sign changes. So inside of here, let's just get this right. Both of these have the exact same form, except one has a plus sign. That gives us the lower single sideband, and then to get the upper single sideband, we have the minus sign. This is still hard to do, believe it or not. It's just not easy. So you can, and this is also known as a phase shift modulator for single sideband. We can move the action of the Hilbert transforming filter down to DC, and then we can build this phase shift modulator, which makes it a little bit easier to implement this. So that's basically, you can see that from the blue boxed equations. We Hilbert transform or don't Hilbert transform, then we multiply by sine or cosine, and then we bring them together, and we bring them together. This plus and minus in here is the pluses and minuses that you see in here. So this constitutes the phase shift modulator. And this guy right in here is known as a quadrature hybrid. In RF circuits, you can buy that off the shelf, a device that you can get a perfect quadrature out of one port, or 90 degrees relative to the other port. So you can get sine and cosine from that. And then you have to just have one Hilbert transforming filter, and this one's going to operate at baseband or at DC. So this can be done, but this is even hard to do. and I'm kind of thinking, where do I want to leave before we take the break? What's hard about building this is it's hard about getting the filter that will not damage DC. So the signum function filter, oops, didn't want to do that. That's the signum function, right? It's positive when f is positive and negative when f is negative. So what happens when you build a real signum function filter that tries to behave this way, it ends up having some problems at DC. It might not pass DC at all. As a matter of fact, it won't, because the definition of the signum function, remember, is 0 at 0. So you can't have DC. And then it carves out a little bit of the frequencies close to DC, either on the negative or the positive side. And in classical amplitude type modulation or linear modulation applications, it's okay for speech to not have DC. We don't convey information, and we don't have super low frequencies we care about preserving in our speech. I mean, if you're a bass guitar player, maybe you want to have about 10 hertz or something like that rumbling in the background in your performance. But to really get intelligibility, we don't speak down at 10 hertz, right? It's just a growl at that point, so we don't care. But in other types of signal processing or modulation schemes, it's unacceptable, and this will be the note that I'm going to leave on. Let's go look at the website. Let's see. I guess I put this on a different computer, so it's not in here yet. So in digital video broadcasting, for example, we took the original analog television broadcasting and we said, TV, well, let's just back up for a second. TV occupies a lot of bandwidth. It has a lot of information in it because it's an image that you want to have lots of detail in, right? And we're in HD and quad, and above that, I think 8K is out there now, right? So lots of information. So when we went to video, though, we have images that don't have a lot of, that are mostly stills, and we need that, you can think of that as being DC information. There's not a lot of motion in the picture. So we definitely need things at DC in a video waveform. So when we first came up with analog ideas, single sideband was not acceptable, and they went to this idea of vestigial. And vestigial, it's a compromise, as this search says, compromise between double sideband and single sideband, mostly to maintain the DC. So in TV, they use 8 VSB, which is a variation on the basic analog VSB concept. I'm definitely not super interested in drilling into that, but I'm just letting you know that even in digital modulation, we have to compromise in order to get it make it bandwidth efficient. So they've maintained the VSB aspect, or the vestigial aspect of it. And vestigial means vestige, so it means a vestige of one of the two sidebands. So you have some crossover, and you can support the DC part of it. Is that interesting? I don't really watch much TV, but if you watch TV, and I don't watch TV at all off of Cheyenne Mountain because I live on the other side of the bluff, up from the Mennonite Church on Union Boulevard. I live in the back side of that bluff, so I don't have a direct line of sight to Cheyenne Mountain. tried putting antennas in my roof. It's still not up high enough. The multipath, the waveform is too corrupted. So my wife let me fiddle with that for about a month or two when we first moved into our house. And she said, I'm getting cable. So it's been that way since then. But does anybody watch TV just using an antenna pointing at Shine Mountain? Okay, so.
It's not very good.
Yeah. So did we waste a lot of money inventing vestigial sideband or this 8VSB? I think it's probably on the way out too, because most people watch it over the internet, and nowadays with Ting and all the other stuff, you know, the fiber optic, people just get it distributed that way. So how does that work? I mean, the whole model changed. Advertising was sold locally, so the radio and TV stations make money off of the local community. If you watch it carried from a long ways away, how does the advertising work? I'm not the business person, but it has to make sense economically, obviously. We're going to take the break now, and then we're going to look at some of the properties of doing single sideband and just see how it works and just hear it a little bit too. So we're at 9:35 thereabouts, so how about 9:45 to 50, that time window? So I'm going to stop the video today because I know it's not going to work otherwise. I guess I'm going to stop it. I'm not confident entirely. Is it working? Okay, it is working. I don't want to mess up because I've recorded videos that are silent videos and they're not fun either. So, okay, let's get back into looking at some more double sideband and demodulation of it, and then we'll do some demos, and eventually we'll wind around and get down to the exam review. So how do we demodulate single sideband? We can use fully coherent demodulation, just like we did with single or double sideband, which is what the telephone company did. They used a fully coherent demodulator. They just simply were doing it to save bandwidth, to put twice as many audio channels on it. So think about how that was set up. Nowadays, we would do different types of multiplexing, and that's what the telephone company moved into, is just switching centers and multiplexing digital waveforms. But in the earlier days, they did multiplex analog. So you can demodulate it, and then here, it's just showing you that putting in the possibility of having a not coherent carrier, what happens? You put in a 4 just because we only have one sideband, so the 4 is to make the amplitude come out correct after we take it all the way down through the multiplication and the trig identities. So here, what goes on at this point is to just say, that represents the single sideband signal. From the analysis just before the break, we just flipped the sign, positive and negative, to be either upper sideband or lower sideband, and then we multiplied by a carrier that may or may not be coherent depending upon theta. And then this is the type of analysis you won't have any exam problems on modulation theory yet, but this is kind of what you do when you're exploring a new modulation scheme, or maybe reinvestigating a variation on something. So these are the types of things that you'll get into in the homework and exam number 2. But here we have the block diagram, so we just implement the block diagram in mathematics. So all I've done is I've said XR of t is what I underlined in red. I have the carrier, the reference signal for cosine coming in at the end, and then I carry it all down to here, and what I'm really missing, and I could put it inside of here, I just didn't do that. See if I can draw some more. Oops. What I don't like about the pencil. So I'm putting LP on there to mean low pass part, because I'm going to assume that I'm going to be eventually, after I do the math to get D of t, I'm going to be wrapping that whole thing with a low pass filter operation. So, but initially I just focus on D of t and see what all the terms are, and then what you do is you look inside, and I'm just spending all this time on it, just saying that, okay, you get this, and you quickly get used to the idea that I'm going to have some double frequency terms, and those are going to get taken out by the low pass filter. So the low pass filter removes those terms, and then you're left with the two baseband terms, m of t cosine theta minus or plus. That's just because of the trig identity now. It becomes a minus or plus sitting over here. So you can track through both upper and lower sideband by just carefully making sure you keep your minus and plus and minus together. And now there it is. And then you say, well, if theta of t is small, or if theta of t is 0, that is gone, and you get back just this. And we're going to look at an example here in the Jupyter Notebook to see exactly what that crosstalk term consists of. It turns out to be for audio applications of single sideband, which is what we have in speech, whether it's amateur radio today or ship-to-ship communications or different things that might still be in the vogue, or in the telephone company, which maybe other parts of the world are still not digitized, because I really don't know what goes on in certain parts of the world where they haven't had the money to upgrade systems. So what do we have? So we'll look at that. There's another approach that's very interesting, and this is kind of the way amateur radio definitely works. It's called carrier reinsertion followed by envelope detection. So rather than multiplying by the carrier, you go through and just add a strong carrier in, and it turns out it just has to be very, very close, and then you can get the information back. You follow it, though, with an envelope detector. So make sure you're noticing there's a very much a difference in these two block diagrams. There's a multiplier and a filter, and here there's a summer and a different box, an envelope detector. So the envelope detector, explore that a little bit, because we'll get into envelope operations, and we'll see that for interference modeling later, and we'll also see envelope detection show up in the next chapter as a way of demodulating a phase frequency modulated signal too. So what does it mean to get back to an envelope? So here I'm just going to jump in and just say, let's study what E of t is. So E of t is our received waveform. In this case, we're focusing on a single sideband waveform. And then we've got pure carrier added in, k times cosine omega ct. So I've got this written now as an what's called an in-phase and quadrature term. In-phase and quadrature meaning that I've got a portion of it is on a cosine carrier, and another portion is on a sine carrier. So those are called in-phase and quadrature because they sit, cosine you can think of as being on the real axis, and sine, because it's rotated 90 degrees, is on the vertical axis. So we have this representation, and we want to construct the envelope. And the envelope is the envelope we saw in the AM signal. And I was looking at that earlier in both the Python model and then on the notes. But how do we get our hands on the envelope? So this next little trip here is to look at how to get the envelope. And then once we get the envelope, we can get our recovered signal. So I'm saying it's a more general problem. And so I'm just going to take a very general scenario here of having A of t cosine minus B of t sine. So the A is called the in-phase component, and the B is called the quadrature component. It's, one's modulating the cosine, and the other one's modulating into the sign carrier. So this is a little bit of a game, but this is getting us into some complex signal modeling. When I say complex, I mean complex arithmetic. So what we can do is we can replace the cosine by an e to the j, and then we're going to take the real part of it, so we'll get back that cosine. In here we'll put in a j e to the j, so that if I take j e to the j and take the real part of that, I'm going to get back a sine. This is just using Euler's identity and the properties of complex exponentials. So to go down to here just requires focusing on what we're doing. We're going to take the real part of something, and that'll get us back to where we started from. And so I'm sort of working in reverse here. I'm trying to synthesize the envelope by this expansion means. So now I can pull the a of t and jb of t out, and then together and factor the e to the j omega ct out. And I'm just telling you that this representation of a real signal, received or transmitted, because it applies in both cases, will be something we can put up on the airwaves, or we can receive on the airwaves. But inside of it, we can model it now as saying it's composed of the so-called complex envelope times the carrier, and then the real part of that. So that is what we want to get our hands on, and just seeing how you could look at that complex envelope as being composed of a real part and an imaginary part, and it's rotating with theta of t, depending upon how A and B are in motion. So the resultant is r of t, and the r of t is the magnitude then of this quantity, which is the square root of the sum of the squares of the real and imaginary parts of the complex envelope. That is what we're after right now. That is the complex envelope, or the real envelope associated with the complex envelope. This is a complex signal at this point, but it has an envelope, a real envelope, which is the square root of the real and imaginary parts. So it's this amplitude of this thing that's rotating around, and it's fluctuating up and down in amplitude. That is the envelope that we're looking for. So how do we get that? An envelope detector will recover r of t. So the envelope detector we already looked at with the diode and the capacitor and the resistor recovers the envelope out of a waveform. How can we see that more clearly? For the single sideband case, we can expand it out now. We can go back to what I started with up here. This is the A of t, and that's the B of t that we have down here. So now we just plug that in, and we get at the envelope, and that's what our envelope detector recovers. And you look at that and you say, I don't know what to do with that, right? It just looks like we've got m of t, which we know that's our message, that's what we want to get at, but we have m hat of t inside of there, and we know that's the Hilbert transform of the message. So we have to get out something that looks like just the message. And the way you can do that is when we reinsert the carrier, we're inserting, get this to a different color again. We can make this reinserted carrier be large. We can push it up there at the receiver, make it sort of swamp out the signal with a large amplitude, and then we have the binomial expansion. And I'm trying to think, have you seen the binomial expansion, or is it in your memory bank somewhere? If I had a mathematical handbook, well, I guess let's just go in here and look. Hey, it's giving me that option. We're speaking the same language, right? Do you know what I'm saying? When you use search engines, you have to know how to speak a language in order to get it to respond to you. As a matter of fact, I think that's probably the most important thing in using a search engine or AI is you have to know how to speak. If you can't speak, what do you get? You get nothing. So, pardon me?
Especially on Bing.
Yeah, and I like using Google much better, but I'm complying with Microsoft. I could change this to be using Google, but at any rate, there it is, right there. Binomial expansion, x plus y to the n. And then it didn't render the equation correctly down here, but maybe this has got some better stuff in it. This is kind of driving off course a little bit. I'm going to go back to the notes. I think they're better. So the idea of the binomial expansion theorem says that when you have x plus y inside of this radical here, we want to make one term dominate. And so we have the first term in square brackets with the k in it is going to be made much larger than the second term. And then what happens is that it dominates. So the binomial expansion will have the first term for large k will be this. The second term is obviously just the k. And then there's these higher order powers out here, but they're going to all have k in the denominator when we do this expanding. So this is the dominant term that comes out. That's what the binomial expansion theorem says, is that the large term dominates, just like a power series expansion, Taylor series expansion. You've seen that in calculus before. So the binomial expansion theorem just says we can approximate it because we're going to make one term dominate. What I would do is I could pull k out and then I could divide through k, so I end up having, see, it's not working for me. You're going to have that, when I factor k out, that term will have a 1 over k squared inside of it, and it will essentially go away or get very tiny. So we get back our message, and we have it on a pedestal again. We have a DC bias on it. So this is, I forgot I put this in here. This is the binomial expansion theorem. Two terms of the expansion. It says 1 plus x, square root of that is 1 plus 1/2 x for x, magnitude of x much less than 1. So that's the scenario we're working in here. So applying that to non-coherent carrier insertion, where we might even put in reinsert a carrier that's just close in frequency, delta of omega or delta f hertz away, we can go through the same expansion idea here, and then our expansion theorem, our complex envelope, is this guy that has the delta of omega in it, and carry that through with the binomial expansion theorem, and we'll get this little thing. This is for a sinusoidal message at frequency omega m, and it will just shift its frequency up and down by a small number of hertz. And for an analog type message, the single sinusoid model is just saying that, hey, we're just going to shift the frequency a little bit, and it's not going to destroy the intelligibility. So I'm going to jump over and just see if you agree or not. But we'll go look in Jupyter. What I just did in my modeling there was I did what I normally would do. I start looking down to find something useful, and I generally start trashing a lot of stuff because I generally don't hit it right the first time. I'm sure there's something much better out there that would have, probably I should have gone to Wikipedia. You guys use Wikipedia more than anything? It'll clear up a lot of the cruddy stuff around your search. At any rate, we can build Hilbert transforming filters in Python. We use a function called remez, and then we specify, inside remez, we get to specify the type, and the type can be, in the remez, notice that there is Hilbert as a type. It's amazing, right? Somebody's thought about this stuff. Oh, it's not amazing, because engineers are before us in time, and they've all recognized this stuff a long time ago. So here is a means of approximating some Hilbert transforming filters. There's the impulse response, and if I look at the frequency response for one of these filters, we see that from 0 up to the folding frequency, it looks very, very flat, but notice, like I was showing you before, there's impairment down here. It's not passing DC, and it's actually carving away some of the response. So I'll probably have you look at that in a problem, is what I'm thinking of. It has a nice linear phase associated with it, and it has a steady 90 degrees on top of that. So it's got a linear phase plus a steady 90 degrees. So let's create a function called analytic signal, which is what we were just talking about earlier. And this function will use the digital Hilbert transforming filter, and I can take a message and I can Hilbert transform it. So this is just a tool in the toolbox. We're going to use, I don't know, do you want to use the UK voice for a change? Yet last time we used female and male US. We could go switch to the UK guy.
The little tales they tell are false. The door was barred, locked, and bolted.
Got it? That's what we're going to be hearing, or we're trying to hear. So I'm going to do the rate change object again, like I did last time. So I'm going to create an analytic signal. This time I'm just going to cut to the chase. I'm going to use exactly the speech file. So here I'm going to use the British speech guy. I'm upsampling the 8,000 kilosample per second speech file by a factor of 12, so it's going to be at 96 kilosamples per second. I'm using my coefficient in my analytic signal forming function to form an upper sideband signal, because I wrote that in there as being upper or lower. And you can see the help associated with that says, takes a string of being upper or lower. So I'm going to create an upper, and there it is, at baseband. So it's the upper sideband, and then there's no mirror image. So this is now a complex, or it's an analytic signal. So I will upconvert it to 24K, and 24 kilosamples per second is the carrier, and there's its envelope. And I just put a little tick mark on here to show that 24 is right here. There's a little bit of slop over because the filter doesn't pass DC, but it does pass a little bit of the negative frequency. So for all practical purposes, it's pretty clean upper sideband. Agreed? You don't see the mirror image down there anymore. So now we're going to coherently demodulate it. And I'm going to coherently demodulate it with the 24 kilohertz. And then I'm going to play it back.
The little tales they tell are false.
It's good to go, right? So now what happens if I don't demodulate that correctly? If I'm going to not quite shift it down in my coherent demodulator, I'm going to go 23,800. So I'm going to be 200 hertz low, so I'm not going to pull it down to baseband as far, so it's going to have a little positive frequency shift in it. The waveform, it's not going to be noticeable, but because I'm only shifting a single sideband, whereas in the double sideband, when we didn't have the perfectly coherent, we heard two speech signals, one on top of the other, one shifted up, one shifted down. It was like a blending of shifted speech, but it sounds pretty obnoxious because they're on top of each other. This will be cleaner.
The little tales they tell are false. The door was barred.
It's just shifted up or down, well. Right? And this is the way.
Right pairs are fit.
This was the nature of single sideband in the early days. So what would happen if I shift it in the other direction? You might like this better. I could take this, shift it off by 300 hertz. You don't really see it in the This is the coherent part, shifted down to baseband. That's the double frequency, which the low-pass filter in here, which is a Butterworth low-pass filter, is getting rid of.
The little tales they tell are false.
This is a little bit more mashed up sounding.
Warped and altered as well. Rice pears are fit for the little tales.
So what you would do is you would manually on a single sideband, say amateur radio, you would tune it manually to get the frequency centered. And Kurt, you've done this, right? So you would just get it so it sounds pleasant. You would not worry about it being coherent. So we could also do it with the carrier reinsertion. So this is the other block diagram. We have our single sideband signal come in, and rather than multiplying, we're going to add in this large carrier. We're going to form the analytic signal, which is going to be a means, and this is what I'm going to have you play with, I think. I just haven't formulated it all. We'll take the real part and delay it, and then we take the Hilbert transform part, which will already have a delay built into it because of the filter. So if we're going to form a fully analytic signal that we can then envelope detect from, we have to delay the real part, because if we form the analytic signal and it's delayed in time and the real part doesn't get delayed in time, now they're way out of alignment and it's not going to work at all. So we have to just physically delay the real part to match the delay that the imaginary part gets with the Hilbert transforming filter. Does that make sense? That you just have to put in a realizability delay on the other signal. So that's this operation here. So we reinsert it. So here we're going to start with the reinsertion. This is k is equal to 2. I'm going to put it up a little bit higher. So we have carrier reinserted with the single sideband signal, and that's what this spike is. And then this is the upper sideband again. And now I'm going to form an analytic signal in the receiver on that signal. Again, strong carrier, and my information is down here. This is not an inefficiency issue because this is being done at the receiver. I'm just doing something to make it easier for me to demodulate it. I'm not wasting power at the transmitter. But again, here's the waveform that I get after I go through the analytic signal creation. So I have positive, I have real and imaginary parts. So I have this analytic signal, which only has the upper sideband. And now I go ahead and recover it.
The little tales they tell are false. The door was barred.
And it works. I mean, again, if we're not perfectly coherent, though, which is what we would not be at the receiver, our demod here might have the same phenomena that we had before. We might be off by say 200 hertz in this case. And what we'd be hearing then as we walk down this path
The little tales they tell are false.
But it still works, and this is the more likely way the amateur radio does it with the carrier reinsertion technique. So I've just taught you some historical things mostly, but it's still interesting because there are things that are still viable in the world today too. I mean, the technology maybe gets replaced by new stuff, but old stuff still has a way of hanging around. And if you are working in industry in the government domain, we have a lot of legacy things out there. We'll probably see where some legacy things maybe are causing failures or things not to work as well. We also have drones and newer technology too. Okay, this is the next topic, and I want to see where we're at time-wise. So we've already talked a little bit about vestigial. This is in the notes. It just says it allows DC to pass. It has bandwidth advantages over double sideband or AM, and it's similar to single sideband. So the primary application was originally analog TV, and then it came up with 8VSB and our digital standard. So this is sort of what the effective response is. If this is the carrier you're going to pass with this gain slope on it, the upper sideband, and then you have a sort of an anti-symmetric negative, and when this lower half, the way I like to visualize it is when this folds around in the demodulation operation, this will fill in that attenuation that you see there. What I'm trying to make you understand is the triangles kind of fit together, and then you get a flat spectrum when you do this vestigial sideband operation. So this spike will get added onto this one, and it will remain flat. So I'm not going to spend the time going through this. This is the antique of the way analog TV used to work. And they're gone. It does not exist in the U.S. anymore, because this was, for me, this was like a major deal. For you guys, you were alive when it happened, but you didn't really pay attention to it, probably because you were just watching cartoons or something, and one day you watched them on a different TV or something was different. But they shut all the analog TV stations off, and they went away. And they were replaced by digital. And I don't think it's really all that impactful thinking about it now, but it did happen. That time came when they went away, whereas AM and FM radio stations have not changed, but now they've been enhanced with some digital means associated with them. Has anybody in here heard of HD radio? High definition radio. There's a standard for AM broadcasting that brings the digital carrier in, and then there's FM. Station I'm thinking of mostly that I might listen to would, because my Toyota RAV4 from 2017 has HD on the FM broadcast band. So if I'm listening to a station like KCME, classical music, it comes up with another digital subcarrier that's available that has a jazz station on it, and both of them have enhanced fidelity. They have higher, better frequency response, crisper sound than you get with the original standard. I can't tell you how it works because it's proprietary. The company that developed it for the United States licenses it to all the radio stations around the country, and it's a secret how it works. I'm telling you, I'm interested in these things. You can't buy a book on how it works because the company makes you pay a lot of money to learn about how it works because they want to hold on to it. At least that's the way it was a few years ago, last time I looked. Okay, spend just a few minutes on this idea because it's important for what's coming up in the lab today, I believe. Frequency translation and mixing. This is a bread and butter topic of communication systems everywhere, where you bring in a signal maybe on frequency F1 and you want to move it to a new frequency. So what we do is we multiply by a local oscillator, a signal that's going to shift the frequency. In this case, its frequency is known as the local oscillator frequency. But if we set it up to be omega-1 plus or minus omega-2, and I'm thinking now in terms of the absolute value, so we don't think of a negative frequency, we just think of a difference frequency, it will take F1 and it will move it to F2, whether it's up or down in frequency. And I do have a little picture of that over here in the Jupyter Notebook, which I'm not going to go through today, but I'm just going to show you what my simulation picture here was. In this particular case, I wanted to receive PC, which is this blue signal. So this carrier signal is set to be so many hertz above this one so that the difference frequency is going to land over here, and that's how my receiver is going to work. It's going to be looking at the so-called intermediate frequency. And a flaw, or just one of the things about frequency translation, is there's always an image signal. So if this was another station that was sitting up above my carrier or local oscillator by the same amount that that's below, it will translate and it will land right on top. So we have to use filters to keep the image signal from getting in. But then there's always a sum frequency, so there's a difference in a sum. So in this case, those are the other things that are produced in the frequency translator, which will be explored in the lab. And those of you taking the lab, that's why we have filters on the boards, was to be able to let you play with things like this and then see how this bandpass filter will just mostly pass the signal of interest after the translation. And the math behind it is not simply amazing. It's pretty straightforward, but it is extremely important. It's used everywhere all the time. People will say LO, meaning local oscillator. It comes in at S-band, which is around 5 gigahertz, and we move it down to 70 megahertz. So what do? We multiply times a carrier, local oscillator that will form a difference at, say, 70 megahertz, and then we introduce some filters and things to keep the unwanted out, and to also make sure if it's in a receiver application, we don't let an image signal come through. In the AM radio that I just gave you, it'll let that happen. I mean, it has a filter, but it's not perfect. So when you hear two stations on top of one another, it might be the image signal is what is leaking in. It's because it's clobbering it, because it's very powerful. Has anybody ever experienced that, listening to anything where you hear one signal on top of the other? It's just a reality, and we want to have...
There's someone on single sideband, and someone else was transmitting a digital mode on a frequency, maybe 1 or 2 megahertz above or below, and the two were mixing, and it sounded really awful.
So, and that has to do with jamming, too. I'm thinking what happened over the weekend when the bombs were dropping in Iraq. Some fighter jet pilots of the U.S. were shot down, right?
In Kuwait. It was friendly fire in Kuwait.
It was?
Yeah. Yep.
I didn't read the article. Well, at any rate, there's a technology issue in there, right? Probably somebody flying that plane said, something's targeting us, and bam, the next thing they knew, they blew up.
Like a radar detector, but a lot more advanced, yeah.
Yes. Well, it could be the other side, though, too. I mean, who has what? But we build these things. I say we because that's what we engineers do. And things are not perfect, right? You have to be very careful with how you do things so you can cause harm, and intentional harm or unintentional harm. Now, I didn't realize that because I just keeping my head down on what I'm doing. That's really sad. It might have been our own technology that caused this then.
It was, yeah.
You guys will take a deep breath and pause for a moment and think about, did I cause this problem or not? I mean, it'll be on your conscience, though. Sad to say, but things like mistakes happen is what it comes down to. So we'll get more into this. This is like the block diagram for this radio over here. This is what it amounts to. With the local oscillator, tunable amplifiers, IF filter, envelope detector, audio amplifier. This is the basic block diagram of a lot of radio devices. This one picks AM broadcast. I'm going to switch off, though, to talk about the exam. So we will return to this later. First off, I'll just say some things about the exam. And this will be on this video, of course, so you'll be able to refer back to it. The exam will be like the old exams. It will be 5 pages. It won't be maybe 4, maybe 6. It will be exactly 5 pages, which follows the pattern of the old exams. It will be, roughly that's 20 points per page to make 100. So you look at the old exam, that's kind of the way it is. Sometimes it might be more, sometimes it might be less. You are going to be allowed to have the crib sheet, and if you want me to bring a few copies, I will bring some, but I'm assuming that you should have them because you should use it to practice with.
You can post it.
Yeah, it's posted. It's on the website.
Oh.
Right here. Remember, we looked at it before. It's right there under course materials, formula sheet. Some of this is not needed right now. This is later in the course, but The first 2 pages there definitely you want. Okay? So you can have that, and then you can write your own, and those of you taking it at the testing center, and I've got to get that registered and everything, but all of you can have one 2-sided sheet. Okay? And you can have a calculator. No.
In addition to the trig sheet, or?
In addition, yes. And if you want to write some notes on these sheets because you found that you like to have some notes right there, I don't mind if you do that either. I'm going to ask you, though, to turn those sheets in. Anything that you've written hand notes on, I want to be turned in. In the class, I'll manage that. The instructions for the testing center, just plan on having that because it's just for me, just in case something weird is happening and I don't know where something ended up on the page and why it got there, that it was messed up or something. The most common thing is somebody makes a careless error and it's like, I don't want to see you do this, but you write on your cheat sheet something that's incorrect and then that converts into a problem that is all messed up, and I will want to try to understand that if that's necessary. Generally, I'd never look at them, but I just feel like I should have them.
Cheat sheet as well.
Yeah, you can do it however you want to do it. Some people like to do microfiche, which used to be common in the library, but you don't even know what microfiche is, right?
I do.
Some of you do?
Where you shrink it down so you can see one.
Yeah, but they used to have catalogs of serials and things that you would go into the reader in the library and you would get an article that was on microfiche was the film, and then it would blow it up and it would print it. That used to be a common thing.
So you had people in here with like a magnifying glass.
You had a reader in the library in the serials catalog room. They still have microfiche in the library, I'm thinking. Yeah.
I'm talking about like for the test though.
Oh, no. Well, no, but some people will create an 8.5 by 11 sheet where it looks like microfiche. It's really tiny. They might write it on a bigger sheet and then shrink it down at the copy center or something like that. Do what you think you want to do. Just make it usable so that you can use it. Don't make it so you can't use it. You can have a scientific calculator, no wireless devices, but if you have a nice calculator, make sure you know how to use it. So don't just grab something that looks powerful, but if you don't know how to use it, it's not going to be good for anything. And that's, that'll be the way the exam is going to go. We're going to meet until a little around 9 or so, and then we'll have a quick break, and then you'll come back. Those of you that are going to take it at the testing center, and please, if you are taking it at the testing center, absolutely let me know, because I only know of 2 people that plan on doing that, and I just want to know because I have to get that information over there. And I'm going to assume that when we take the break, those of you that are going to go to the testing center will go to the testing center and do it, because that's one of the requirements I'm going to specify. It has to be taken within a very close time interval to when the class is going to take it. That makes sense, right? But don't.
It's going to take a long time. Look at the answers. Got it.
No. That's the control of the testing center. Here, yeah, I'm going to be watching that. You're going to be sitting in here, and then you're going to go work it, and then you'll leave, and I'll have all the papers when you leave next Tuesday, right? So I said 5 pages. I said the cheat sheet for the book, and then your own 2-sided page. Everybody got that part of it?
And the content is from day 1 till today?
No, it's not.
Okay.
That's what we decided upon 2 weeks ago, I think, or a week ago.
Chapter 2.
It's chapter 2 only, and it's only the topics we covered out of chapter 2. So if we go back to the notes, for example, like we just did this today, but so that's not on the exam. And it's not really as much of this material. It's what I gave you homework problems on, the types of problems that I gave you, the ones that are on the example exams that apply as well. So that's what I want to go spend the next few minutes looking at, is what do I have on the website. So first off,
And the quizzes as well.
yeah, that's why I want to look at that first. So this is a fairly, I'll say, ripe area in that I didn't give you the solution. So if I feel so inclined, because I've been looking at old exams already myself, and I realized that most of the old exams spend a lot of time in chapter 3. And I said I wouldn't do that. So I've got to come up with more material from just chapter 2. But I'm going to stay true to form. So what, like it or not, you're going to have more drill down on things that maybe aren't as much fun and not as easy, but it's going to be just the way it's going to have to be. So I'm pretty much planning on taking something, 1 or 2 problems. I mean, you look at these quizzes, there was always 2 parts. So I'm pretty much assured in my mind that I'm going to pick at least 1 page. It might be like this upper part of this problem and the lower part of another one of all the sample quizzes here that I will put on the exam. Does that sound good?
Yes.
That encourages you to study it, right, and practice with it. And I'm just going to let you be on your own, not your honor, but your own due diligence to say, yeah, I'm going to look at this because there's a chance that this or any of them could show up.
All 5 quizzes are fair game, is what you're saying.
I'm saying at least 2 half pages. I'm guaranteeing you that.
So you're not telling us which ones?
No.
All 5 are fair game.
Yeah, that's right. You're right about that. Yeah, absolutely. So think about these, because these were done in the same means. They were done over 15 minutes in class. That's the way that these quizzes were taken. And so you've got this type of thing to deal with. Autocorrelation function. It may not be on the old exams, but it's definitely going to be on this one because we're drilling into just what we covered in chapter 2. So now I have the old exams I can look at for a little over 5 minutes here. Is there any one of the old exams which anybody already looked at and thinks they'd like to look at right now? I'm going to look at one of them. I'll look at the most recent one.
I just had a question about the first exam.
Oh, okay. Well, I'll open up the other one too.
Is that one, that derivative right there? It'll
Yeah.
just be apparent if you ask us about that. That's the derivative of the other function. It's not you. But that's all it is. Can you clearly explain that?
It'll be similar to this problem if I was to do it, but I won't. None of these problems are going to be on the exam because they're on the old exams.
Right.
But I have a history. I mean, I have a inventory of a lot of old exams. So
I just don't like assuming things. I'm just like saying, like, it'll be, oh, this is the derivative of that. It'll be clearly explained, like that question there.
yeah. So this one wasn't good enough explanation, is what you're saying?
No, I'm just making sure it is. That's why.
Oh, okay. Well, it's in the box, right? It says DDT or whatever goes in is what comes out.
Yes.
Is everybody understanding his question? Because I'm not sure. I think I'm
I'm just asking
understanding.
if that box will be included.
Oh, definitely. Yeah.
Sure.
And because I want you to be able to read block diagrams too, because that's kind of the way comm systems works with the block diagram. I get asked that question where I'm working right now. When I come back from my trip, I expect to have a block diagram, and I expect you to have tested some sample code. I mean, blah, blah, blah. Managers like pictures, just like you like pictures, don't you? Technical stuff is pictures, so yeah. Any other question, though, on like, this one was when I first got my iPad, and I started drawing pictures. I mean, I started drawing solutions out of my iPad. So these types of problems are legit, but you can see right here, spectral density, yes. Transmit spectrum, yes. But then this is flagged because this is what we just started talking about, coherent receiver. That's chapter 3. So just all of these sample exams jump into chapter 3. But I could have you draw a transmitted signal because it's just the spectrum of this waveform. But specifically, questions related to modulation theory is chapter 3. And then this is all chapter 3, and then analytic signal that we just covered today. So I'm taking that off the table. Exam 2 will be packed with modulation theory from chapter 3 and chapter 4, just the nature of of the way that's going to work. And I've got to figure out how that's going to happen too with my trip and so on. Okay, any other questions you want to look at in particular? I've got one more thing I have to tell you that's really important to you. You can ask me up in office hours up in the lab too. Another thing I want to tell you then is that next Monday I'm going up to Denver to have a biopsy done of bone tissue in my pelvis. I'm thinking they don't think it's cancer, but they're going to find out. So, but at any rate, the procedure, I'm not looking forward to it. I'm going to get knocked out. Not totally, but I'm supposed to be down for the rest of the afternoon. And I'm going to be recovering. My wife has to take me and bring me back home again. So I'm saying that don't expect me to respond to things past the morning, because I'll be leaving probably by 10:30 or something like that to go up there, and I'm going to be out of it. I'm told I'm going to be out of it, and I'm just going to expect that maybe I'm going to be in pain too. I don't know. This is not a laser guided needle, but it's a let's see. It's not an MRI, but what's the other scan type that we get? Pardon me? Yeah, CT. It's a CT guided biopsy, and my wife has had that before too, but I've never had such a thing. So I had PRP injection, and that was guided by ultrasound. Everybody heard of PRP? That's where you have a tissue that doesn't want to heal, and I had a gluteal tendon issue and guided that right in and put some of my blood into me, spun down as a plasma, and it was very successful. The MRI they took of that part of my body revealed these spots that are on my bones, and then they started watching them. So then it's got bigger. So now they want us to figure out what's going on. I'm excited. I'm not excited about it, but I have to do it. So it's kind of cool, though, that you can be doing something. It's called incidental find, and my other doctor that I have said any of us could have an incidental find on any scan of any part of our body, and then they jump up and down and get excited and want to do something. So I'm just going with the flow, and I'm anxious that it's going to happen and get it behind me. So hopefully it goes well. So that's just that bit of note. If you've got to have calories and things like that while you're doing your exam, or caffeine or something like that, just plan ahead. You'll be able to run out and get something. I know we're not going to take a long break, and I don't want you to get carried away with that stuff. Like if you need to go get some coffee or need to get a snack, please have that, though, in the room here, and get back so we can get started and get this done. So 5 pages. Just they'll be focused on chapter 2.
5 pages, do you mean like 5 problems?
No, approximately 10 problems. Or it might be a long problem that has parts A, B, C, and D. Yeah, 5 pages though. Approximately 20 points per page to make 100 points. Does that sound good?
Is there extra credit on there?
No, I'm not on the exams.
Just on homework?
Yeah, there's pros and cons, right? If I have 10 problems might be more advantageous because you can get partial credit, and if you get lost in the weeds, you might not crash on the second half of the long problem. So that's a trade-off in there too for both me and you. So, okay, we'll see some of you up in lab, and we'll get out of here.